In this video, we'll take a closer look at the difference between the Fourier transform and the Fourier series. As we've already learned, the Fourier transform is applicable to signals that are not periodic, and the Fourier series is applicable to signals that are periodic. Let's do a side-by-side comparison, and hopefully that side-by-side comparison will help us tease apart exactly how they're different. So let's start with the non-periodic signal to the right. To the left, and we can calculate the Fourier transform for that according to the integral, which will be integral from -1 to 1 of x of t, whose value is the constant 1, e to the minus j omega t dt, which we can then solve. And we can actually skip the math because we know from experience that what we're going to get is 2 sine omega over omega. Now, that was easy enough. We'll come back to that in a minute and talk about what that means. Now, on the right-hand side, we have a periodic signal. And if we do that one, instead of a of omega, we have a sub n. And according to formula, that's going to be 1 over the period times the integral of 1 period. So in our case, the period, let's go ahead and substitute in the period. In our case, the period is 4 seconds. It repeats every 4 seconds. So we're getting that by inspection. So the Fourier transform is going to, the Fourier series is going to be 1 over 4 times the integral from -1 to 1 of the constant 1, e to the minus j, times the frequency, which is 2 pi over 4 times n, t dt, and I'll spare you the math. You can work this out on your own time, but what you should get is 1 over pi n times sine of pi n over 2, where n is equal to 0, 1, 2, dot, dot, dot. Okay? Now, let's talk about how we use both of these Fourier transform and Fourier series to work backward and calculate the actual signal. And it's probably easier to start in the case of the periodic signal. So in the periodic signal, what we have is a sum of cosines. All right. So the first cosine we have is actually the 0 cosine, the DC offset, which in our case is going to be equal to 1/2. Okay, that's your a sub 0. And then we're going to have the cosine that corresponds to n equals 1. So we'll have 2 times the absolute value of a sub 1 times cosine of omega 1, which is 2 pi over 4 times t, plus the phase angle of a sub 1. So all of that is for the n equals 1 term. So let's go ahead and label this. This is the n equals 0 term. And then all of this is for the n equals 1 term. This whole cosine right here is for the n equals 1 term. And this term here is omega 1. Okay, keeping in mind that omega sub n is 2 pi over 4, in this case, times n. So what I want you to realize is that this sum only exists for integer multiples of n. Okay, so what's the next cosine in this sum going to be? It's going to be 2 times the absolute value of a sub 2 times the cosine of 2 pi over 4 times 2 t plus angle of a sub 2. Okay, so this whole bit over here now, that all corresponds to n equals 2, and this frequency here is omega sub 2. So the point is that, and then there's obviously going to be an infinite number of these, all the way out to n equals infinity. So the point here is that x of t can be expressed as a sum of cosines restricted to, so the restriction is that we can only have energy at frequency omega sub n. Okay, only those frequencies. Okay, and again, those are 2 pi over the period times n. Okay, all other frequencies, there's no energy. So what this means is that we can express x of t as a sum. Okay, essentially x of t, if we're thinking about it with mathematical notation, can be expressed as a sigma. Now, back to the non-periodic signal, it's a little bit trickier. So if I were to go ahead and make a plot of A of omega, it would look something like this. All right, that number would be 2. This would be frequency pi, 2 pi, 3 pi, and so on. So what you can see here is that whereas before there was only energy at specific values of omega, now there's energy at all values of omega, okay, or with the exception of just a couple ones that are zeroed. But basically omega exists everywhere. So in other words, I could pick some frequency here, okay? Let's call that, I don't know, 1. Okay, omega equals 1. So just that one particular point is going to donate the following. It's going to donate 2 times the absolute value of A of 1 times cosine of the frequency 1 times t plus angle of A of 1. Okay, so all of that cosine corresponds to just that point. Now, here's another cosine. Okay, here's another cosine. Let's say this corresponds to frequency 1.1. So that's going to contribute, that point is going to contribute 2 times the absolute value of A of 1.1 times cosine of 1.1 times t plus let's try that again, plus A of angle of A of 1.1. And what else do I do? I'm probably going to have a point here. Okay, that's going to be a cosine, and that's going to be a cosine. And I forgot that between 1 and 1.1, I could also put a cosine there. In fact, there's an infinity of cosines. All right, and that means that in the end, we're not going to be doing a sum. Okay, this doesn't lend itself mathematically to a sum. Okay, this is not a sum. It's not a sum over sigma. Sorry, over frequency omega. But rather, it's an integral. Okay? It's an integral with respect to d omega. Okay? So really what I'm going to have is an infinite number of these cosines, and they're all going to be times d omega, and then I'm going to integrate over all values of omega. That is a highly unusual way of expressing it, but that's the basic idea. So the question now is, how do we actually present that in MATLAB? Or in any computing environment, really? Well, the good news is it's not that hard. Remember that anytime you do a numerical integration, okay, let's say this is some arbitrary signal x of t, and let's say this is dt, and we're going to do a numerical estimate of the integral. Really all we're doing is we're going to take rectangles and we're going to add together the area of those rectangles. Okay, some rectangles will be taller, some rectangles will be shorter, but we're going to add together the area of each rectangle. Okay, so the width is delta x and the height is x of t. And in the limit that delta x goes to 0, as long as you use a pretty small value of delta x, then this sum of rectangles will be approximately the same as the integral. Okay, sorry, this probably should have been dt and not dx. I shouldn't mix my metaphors here. Okay, so that rectangle will approximate the integral dt as long as delta t is small. Okay, so that's exactly what we're going to do. When we go to rebuild this signal x of t in the computer, we're basically going to do this sum. We're going to pick a bunch of discrete values for omega, and then we're just going to sum them together, and we're not going to forget our d omega, right? Because if we forget the d omega, then we're not computing areas. We're computing sums. So let's go ahead and give this a shot and see how this goes. So in MATLAB, let's start with the Fourier series. You can see that here's my definition of A. That's exactly the one that we calculated by hand. Here's my formula for the frequency. Here's my DC offset that I'm going to use to initialize x. And then I'm just going to loop through 100 harmonics. And in each case, I'm going to calculate the frequency of the nth harmonic. That comes from the formula on line 5. And I'm going to calculate the magnitude and the phase. That's going to come from the formula on line 4. I'm going to add them together, and I'm going to plot. And when I do that, you can see that I get exactly what I'm supposed to get. Okay, that's exactly the same thing that we started with the exception that obviously I only went to 100 harmonics. If I'd gone up to infinity harmonics, these edges would be perfectly sharp. Now, by way of comparison, let's look at the Fourier transform. So first things first, I generated the MATLAB function, the sync function that's built into MATLAB has a pi term built into it that we don't really want. We just want sync of x to mean sine x over x. In MATLAB it means sine pi x over pi x. So I created my own version of sync here that divides out the pi. So here we are. Here's my formula for A. It's 2 sync of 2 pi f, where f is the frequency. We used omega when we did the hand calculation, but here when I do the integral, I'm going to use frequency. So I define time. I have my df. Here's my initial frequency, sorry, my DC offset. And here I go. Each pass through the loop, I'm going to create a cosine with frequency 2 pi f, magnitude determined by A, and phase angle determined by A. And then I'm going to take that height of the rectangle, I'm going to multiply it by the width of the rectangle, and then that's it. I'm just going to iterate through the loop. So you can see whereas before, when I was doing the series, I was iterating over harmonic number. Now I'm iterating over frequency. This is a numerical integration. Before I was doing a sum, now I'm doing a numerical integration. They kind of look the same, but they're different. And when I run this section, you can see that I get exactly what I wanted. Okay, I get a pulse that goes from -1 to 1, the height is correct, and so on. If I wanted to get a more precise pulse, all I would need to do was go out to a higher frequency. So you can see that if I went out to 100, I would take a little longer to run, but eventually I would get what looks like an even better approximation to my original signal. So hopefully that helps underscore some of the differences between the Fourier transform and the Fourier series, especially with respect to how we represent them in a computing environment such as MATLAB.